The talk I have been asked to talk about the MYRRHA, the present status, and I said to Andreas and Thomas when they asked me to say something, I said I will say more specifically some characteristic of our Mira accelerator because of this very particular needs that we have when we deal with ADS. So first thing that in September 2018, the Belgian government decided to build the Mira facility in MOL as an international research infrastructure. He allocated the budget of 558 million euro for the period of 19 to 38. All that is not for CapEx investment. The CapEx covers in the period 1926 what we call the Minerva. I will or Mira phase 1. I will show you what is that. We are going to continue the R&D and design of the what we call phase 2, which is the upgrade of the accelerator to 600 MeV, and phase 3, the reactor of Mira. We succeeded also to secure already some operational cost for the phase 1 we are going to build by 2026 in the present planning. We have been also successful in convincing our government that we need to create a non-profit organization which will be called MYRRHA ADS. This is a legal structure, Belgian legal structure for international non-profit organizations. And the purpose of this is to welcome the international partnership in this project. And also we got that our tutorship ministers, 3 of them, means energy, economy, and science policy, will be in charge of the promotion of the international consortium as well as the IESBL we are creating. So Mira, I look for my laser pointer. This works very good. Is coupling a subcritical reactor, which is working with a fast spectrum. Therefore, we use as a coolant for our reactor lead bismuth tactic, which is a heavy metal, but with the melting temperature rather low, 123 degree and C, and but it is subcritical. This means that it doesn't contain enough fissile material to sustain the chain reaction. As such, we need an external neutron source to be created in the center of the reactor for maintaining, starting for the chain reaction and maintaining it as long as this external source is created. And how we create this external source in the center of the reactor? Through bombarding with a high proton, actually power accelerator, the liquid lead bismuth of the coolant in the center of the reactor core, and we do create primary neutrons by spallation reactions. It's like we do in spallation sources such as in SNS in Oak Ridge, or the one of J-Park in the MLF, or in PSI, where we are welcomed this evening in SynQ. So we shoot the powerful proton beam on a heavy metal to create spallation source. Here in Mira, we put that spallation source in the center of the reactor, which is subcritical. And the purpose to do so, so the accelerator of Mira is 600 MeV as the upper energy, and a current of 4 milliamp, which is the nominal value. The reactor with 600 MeV, you have a penetration depth of about 13 centimeter, and the footprint of the beam is about 70 millimeters. So that gives you an idea, half a liter where you shoot 2.4 megawatt power. So that you have to take away. The purpose of MYRRHA as accelerator-driven system, we call it. This is the concept of ADS, coupling subcritical reactor with a linear accelerator or cyclotron or synchrotron, but here we choose linear accelerator. We'll come back on that. And the purpose of this is to go to transmute minor actinide for the treatment of the high-level waste through the transmutation. I will come back on those also, and to demonstrate the ADS concept at what we call pre-industrial scale, means a power ranging between 50 to 100 megawatt thermal, and our design presently is about 100 megawatt thermal as maximum power. So we call phase one the accelerator until 100 MeV. We couple it to an experimental facility. I'll come back on that. The phase two is upgrading the accelerator to 600 MeV, and the phase three, the reactor. So a portfolio of applications of this ADS MYRRHA experimental machine is manifold: medical radioisotope production, fission energy Gen 4 systems where we look for material that we could need for these futuristic systems, and fundamental research thanks to the large accelerator we are having. Fusion material is a big challenge, so we create conditions where we can test material for fusion. But the major application is, the flagship application is the treatment of the spent nuclear fuel or the nuclear waste. And what we are willing to do, actually, when we do use nuclear fuel in our power plants today, in the thermal reactors, we are using an oxide fuel containing uranium-235 and uranium-238, about an enrichment ranging between 3.5% to 4.5% of uranium-235. And when you shoot neutrons on this U-235, you create a fission that gives you two fission products and about, on average, 2.3 neutrons. And one of the neutrons, you would like to keep it to make the next fission. That's why we speak about a chain reaction. But we have the other isotope of uranium that can capture a neutron and become a heavier element. And the heavier elements we are creating is, first of all, neptunium that decays to plutonium, then goes further to americium by capturing and curium. The plutonium, we call it the major actinide, and these three others, we call them minor actinide. And these actually minor actinides are also, the plutonium is a burden in the nuclear waste if you are not doing reprocessing, because we do reprocessing. Some countries do that, some others are not, but you can retrieve the remnants of uranium in your fuel and the plutonium and reuse them for making again fuel with that. And you leave in your waste flow the minor actinide plus the fission products. So these are the ones causing us very high radiotoxicity and also a heat load in our nuclear waste, which is then conditioning the dimensions of the footprint of our geological disposal if we go to geological disposal. And how this translates, as I said, putting uranium ore in our present day reactors, we increase the radiotoxicity by a factor 1,000. That you can't do anything about it. That's the way it works. If you just go with that used fuel, put it underground, it will take you about 300,000 years to get back to the original radiotoxicity of the uranium ore you took from nature. You do reprocessing, means that you retrieve uranium and plutonium, that you refabricate a new fuel with that. This is an existing technology. There is nothing to invent. It is applied in various countries. We applied it in Belgium during a certain period. We applied it in Switzerland, MOX in the reactors. We do it in France today. We have done it in Japan. So this is in light water. But originally, the MOX was foreseen to go in fast reactors. But we didn't develop rapidly enough the fast reactors. Therefore, we said we can already start doing reprocessing and recycling in the existing reactor technology. But if you take away the minor actinide, from the vitrified waste contain minor actinide and fission product. You drop from 300,000 to 10,000 years. And if you take away the minor actinide and you do something with that, means just transmuting them through fission, you can drop to 300. That's what is the thing that we are willing to demonstrate at pre-industrial scale, because at lab scale, we did already the job. And the purpose to go to pre-industrial scale is to put then the economic values towards the industrialization. From the lab scale, we can't project how much will it cost industrially. You need this pre-industrial scale. And Mira, for the transmutation, is this part of the pre-industrial scale. We have to do that for the advanced separation. We have to do that for fuel fabrication. And we have to do that also for the reprocessing of this heavily loaded minor actinide fuel. But today I will not lecture about the transmutation and the waste management. I wanted to focus about the accelerator specificity for ADS. These are the characteristics of the Mira Accelerator, 600 MeV, 4 milliamp, but CW. And this is, you can say it's, well, technologies that is today existing and we are used for this kind, but CW high current like this and not in pulse, that is what is tricky for us. And even more demanding is this, the reliability of the beam we are requesting. Because as I said, if we shut down our accelerator, the reactor will stop. So we are not making any transmutation then. So, and today when we look at the large accelerators like the one we are willing to realize, if I look the one of J-Park, we were monitoring the number of beam trips over there, as well as the one of SNS in Oak Ridge. And we found that compared to what we are demanding in beam trips longer than 3 seconds, where we would like to have 10 maximum per 3 months of operation, we are 2 decades below what today's large accelerators are doing. So we need to improve drastically this reliability. Shorter beam trips we can manage with the thermal inertia of our reactor. But these longer trips means this is what we call in classical jargon of reactor people a scram, an unforeseen shutdown of your reactor. Then you need a certain lengthy procedures to respect from the safety point of view. And it can go between, I would say, few hours up to 2 days before you can restart. And if I take J-Park or SNS, they trip about 2,000 times per year. This means if I just take half a day to restart, I need years on Earth of 1,000 days, which is not the case. So we need to improve this reliability. And so the idea to improve I don't know what happens with this slide. It was supposed to be, let me see, why it doesn't show, sorry. Oh, the figure disappeared. Well, I wanted to show you the various existing accelerators in this beam, let's say, power, and what is supposed to be appearing here close to the cyclotron of PSI, 590 MeV, nearly 2 milliamp is very close. And we have also the accelerator of SNS, which is very close to us. So that's what I see. You see here, PSI and SNS are the two closest, and the one of MYRRHA should be here, about actually 600 MeV, and the current about 4 milliamp. I apologize for this, I don't understand. It was working just a few minutes ago. But nevertheless, that gives you an idea. We have larger accelerators in terms of current and energy, but there are existing machines in the kind of the one we are targeting to make. So what we have decided to do is to demonstrate this reliability. We worked very hard on the individual components. I will come back on this. And so, but what we decided in 2015, we said we will create MYRRHA in 3 stages. Phase 1, the accelerator up to 100 MeV, but with 1 injector line, not 2. The double injector is to create redundancy in the low energy part to achieve this reliability we are targeting. And from 17 MeV to 100 MeV, we will go with spoke cavities. I will come back on this. And then from here with niobium elliptic cavities, maybe in this part between 100 to 200, we are watching what's going on in the ESS project with the double spoke cavities that they are testing for the moment, if this can do the job. And the idea to have this first facility built is to have the first experimental facility by 2026 on the site of MOL, and then go further for phase 2 and phase 3. Spreading this investment will reduce the technical risk about the reliability. If we can't demonstrate by 26 or 27 this needed reliability, can design a second injector that will be doing the job certainly for us. From the simulation, we have seen that that can be delivering the work, but we would like to use the measured data with this injector up to 100 MeV in order to qualify or to verify our modeling that is correct, which will allow us then projecting the full reliability of our accelerator. So the fault tolerance, we apply it up to 17 MeV by redundancy. So duplicating the injector up to 17 MeV, and we've switched between the 2 injectors. We keep the second one in hot standby, but we operate only with 1. And if we lose the injector, we switch on instantaneously the second one. From there on, the serial redundancy will be applied in the superconducting spoke cavities. We have many identical cavities which are in series, but we do not exploit them at full capacity. We derate the level of those cavities, let's say to 70–75% of their maximum capacity. And if we lose a cavity, then we do a local compensation, but we need then a very rapid adaptation of the adjacent cavities in terms of gain in acceleration. And so this will be allowing us to reach these beam trips that we are targeting of about 10 at maximum in 3 months. You will tell me why 3 months? 3 months is the period of operating the Mira subcritical reactor without, I mean, the cycle of the machine is 3 months. And we wanted in that 3-month operation at maximum 10 scrams, if I can call them this way in my jargon of reactor people, in 3 months, which is still high, but for an experimental machine, it's okay. We can live with that. We prefer to have 0. That's, I tell you, that's what our objective is. But we are building a first of a kind. Today, our research reactor BR2, which is 100 megawatt, we seldomly experience unforeseen scram, but it happens that we have 1 scram per cycle of 28 days. But in general, we do not experience unforeseen scrams. So here we are a bit more, let's say, tolerant, 3 scrams per month, but we hope that we will do better. But then this means that we have a control system must be able to reconfigure and safely recommission to full power. This is also something that we have to develop in so derating, duplicating for the injector, the redundancy, serial redundancy with derating the cavities, and readjusting locally the compensation with the neighboring cavities. But you need then to have a control system which is capable to adjust so rapidly. So that's the strategy we are doing in what we are calling the fault tolerance. And to demonstrate that, so as I said, we will build the stage 1, the accelerator 200 MeV with 1 injector. And all the components have been now created, prototyped and tested. This is the ECR Source you see. It has been, now it's operational in the site of Louvain-la-Neuve, the low energy beam transport line. The forward RFQ has been designed together with the German colleagues from IAP Frankfurt. These are with the colleagues of Pontechnique for the source and LABT with LPSA in Grenoble. The CH cavities also with IAP Frankfurt and Bevatec. We have designed them and prototyped them, and this is already operational in Louvain-la-Neuve. We are busy with the CH cavities to install them also in there. From there on, we go for spoke cavities. We have 2 spoke cavities per cryo module that we prototype those, we tested them individually, and now we are prototyping 2, or have been prototyped 2 other new ones that will go in a cryo module for testing in the prototype cryo module, which is also created. So the single spoke cavities designed and prototyped by IPNO in Orsay, as I said, solid state amplifier, first compact up to 160 megahertz from IBA. This is solid state amplifiers, and also the CH cavities for the injector has been also prototyped. The cryo module also is now prototyped. I will come back later on this. So this is installed already in the Louvain-la-Neuve, and the CH cavities will be tested also in there, that you see in the casemate where we are in Louvain-la-Neuve, the ECR source and the RFQ, and normally we can go further there with the CH cavities. This is the first ion source operation in 2019. Then this is the PTF as it will be looking for, the proton target facility. You see the entrance of the beam. Sorry, I have to activate back my laser. So the beam line is going further on towards the reactor, which is over there. And here we enter in the PTF, and we will have a radioactive ion beam, an isol system, as well as a normal irradiation with protons. And we have an experimental hall in this building. We will have a fusion target also in separated building I will not, because we say here we do fusion material, it will be combined with our full beam power. This is the footprint that we will be having. The Minerva, what we call Minerva, is this phase one of the accelerator and the PTF and the full power beam dump, and also combined with the fusion target. And then later on, stage two, the Mira Accelerator continuation. The RF gallery is in here. Then the reactor building is over there. This is how it will be implemented on our site, the master plan. So those are existing buildings, and our BR2 research reactor is over here. And these are the material testing labs, hot labs, like Tfilac in PSI, Andreas. So the RFQ installed, and the first protons have been accelerated on 30th of June 2020 already. Then later on, and last year, despite the COVID, we could successfully create the prototype of our cryo module with French colleagues of SDMS. And it is now shipped to the lab where the testing will be conducted. It's also in France. And the testing of the RFQ at the conditions of Mira has been achieved in December last year, where we showed that we can accelerate until 1.5 MeV at the exit of the RFQ with transmission of 90% through the RFQ. The beam duty cycle is what we were expecting to have, and also these holes that we need to create in the, I told you it's CW, but we need every 4 milliseconds, we need to get a hole in the beam of about 200 microseconds, and this is needed for measuring the subcriticality level of our reactor. And we showed that we can do this in a correct way with our accelerator. So all this is very promising. And now just the global planning for Minerva for the phase one is we are today around here. So the PTF basic design is under work, and also for the accelerator to be finished by the end of this year. And the detailed LINAC building and also the accelerator should be finished by 24, as well as for the PTF for 25, Q4. Then the construction will be launched for the LINAC in 22, and will be more the end of 22. The accelerator itself, well, but the building of the accelerator will be the first break of the ground and 22. Then we end up the construction by 25, 26. Well, now depending the impact of COVID, we are seeing some delays. So we are assessing how much this will be causing as delay. And then we normally foresee that the first protons get out of the LINAC by the end of 26, whereas in the PTF, the use of them by the end of 27. The reactor, we are not forgetting it. As I told you, we are working on it also. And the purpose of the reactor is a series of also work, transportation for sure, the radioisotope also production in that facility, fusion material, R&D, and fission technology platform for the lead bismuth reactor technology. And the purpose is that should be operational by 36. And I speed up. This is just to show you the core, which is multi-purpose. We have material irradiation. We have the fuel assemblies are hexagonal, typical fast reactor assemblies. Then we have also control rods, because we have foreseen that it can be operated also. And by demand by our safety authority, we should start it as a critical reactor before we turn it subcritical. just for the commissioning, even though we have to do it this way. And there are highlights and progress. I will, due to the time, maybe limitation, I should be careful. We have many infrastructures which are built in our technology hall for the reactor lead bismuth technology. This is what we call the baby Mira. We have already a zero power reactor with lead coupled with a proton generator. We do use DT reaction instead of spallation reactions in the center of this zero power reactor. It's about 500 watt actually, where we do all the physics we need for validation and verification of our design codes and for the licensing of the Mira reactor. The various stages for the reactor, we finished last year the design of the primary circuit of the reactor, fully integrated and now frozen. And we are working by the end of 22 to get all the auxiliaries, the buildings, etc., conceptual design finished. Then we enter in the all, oh, sorry, I see that this is Dutch. I apologize for this. By 24, we get actually finishing the costing of our new design and with uncertainty, and then we can enter in the preliminary safety assessment report preparation. We will be also doing the pre-licensing in this period until 24. We have defined that with our licensing authority. We are doing that since 2011 with the objective that we get an opinion from the safety authority somewhere around 26. And then we can enter in the basic design of all the facility with the help of a consortium partner that we need to secure by 2024, with the objective to have the decision for the constructions permit, by 2030. We are on the S3 roadmap, and we are in the final assessment for what we call to qualify to landmark. Hopefully this will be going well, and we are having our last hearing in 2 weeks from now, or 20 days on the 26th. We are going to that. We are also in the set plan, and we are also embedded in the national equivalent programs. I mean, the National Pact for the Strategic Investment of Belgium, we are in there, and also in the Integrated National Energy and Climate Plan that we have submitted to the European Commission as part of the Belgian contribution to the energy plan and climate for Europe. We have very large network of universities working with us. We have also research centra working with us from different countries, etc. And also industrial partners and beyond Europe. We have also works with some labs of DOE, and JAEA is also very important partner for us, and also Korea, South Korea, we have collaborations with them. With all this, once again, I see that this is Dutch, but this is international also language. We are Belgium with this decision. We look to break the ground in 22 already with the phase 1. And we want to also, despite the fact that we are going out of nuclear energy today, that Belgium is very keen to hold competencies and know-how in the country in nuclear, and not only by theoretical education and training, but also with very strong research program sustained by such an ambitious investment in the field. But looking for solutions to society challenges such as the nuclear waste or nuclear medicine and treatment, and also calling for international collaborations. Therefore, we open this project for participation from international partners. And the ISBL that I am talking about is in the final stage to be created. Hopefully, within a few months, we will be making the announcement and inviting countries to enter with us. We wrote with my colleague Jean-Paul Poncelet a book on MYRRHA. This is in French, published by the Royal Academy of Belgium, but we are preparing a version in English, MYRRHA, another look on nuclear energy, that if there are French-speaking people, you can get that book. If you are English-speaking, Dutch-speaking, you have to be patient still 1 month and you will get it. So now I invite you to a little walk in the future. Voilà,